Welcome back. This is week 4. Here's an example. This is out of our textbook Thompson. We have the following data are given for a vibrating system with viscous damping. The weight is 10 pounds. The spring has a stiffness of 30 pounds per inch, and the damping is 0.12 pounds per inch per second. Determine the log decrement and the ratio of any two successive amplitudes. Alright, so first off, let's write off some of our information. We have 10 pounds. We'll know that we're going to have to turn those into a mass. I'll have a spring constant of 30 pounds per inch, but I would rather have that in US units, so we'll go 12 inches per foot. Right, and we'll see that those will cancel out, turned it into 360 pounds per foot. I'll write it down here. C is 0.12, and I don't like the units they gave. Usually we have pound second per inch. The way to remember this is that we multiply C times the velocity to get a force. So you would have seconds per inch because the velocity would be like inches per second. But we'd rather have it in feet, so we're going to multiply this also by 12 inches per foot. And in a similar way, that goes away. So it comes out to 1.440, and these are pound seconds per foot instead of inches. The natural frequency, undamped natural frequency, is going to be K over M, square root of K over M. So I have the square root. Let's see if we get the units right just to practice here. 10 pounds, right? But we need to, no, I'm sorry, it needs to be K. My bad. Of course it's my bad. There's nobody else here. Pounds per foot divided by mass, which is 10 pounds, but we need to divide it by 32 by 2, so it would show up right here. What the hell's going on? My brain's not working. 32.2, and those are feet per second squared, right? Make that longer. I like to cancel things out other colors. Using red too much. Pounds cancel out. This is a per foot times a foot, so that cancels out. So we end up with the square root of 1 over second squared, which would totally give us radians per second. So we have 34.05 radians per second circular natural frequency undamped. To be able to find the critical damping, a couple different formulas, but this is the most straightforward. Once we have that natural frequency, that's the easiest one to use. So we go 2, and then let's go to the mass. Once again, we have 10 pounds per 32.2 feet. And then I almost think about putting the second square up at the top, but I'll write it down there, second squared. Boom. And then we have times 34.05 radians per second. And what we'll find here, let's see if we do this right. Yes. Okay, so everything will work out when we get the number to go 21.15, and you'll see that we have a pound second per foot, which is what we expect. So therefore we get, let's change to green now. We'll get very colorful. We're going to have C over CC, which is the definition of the damping factor, 1.440 divided by 21.15, which will be equal to 0.06809. Right, so that's very slight damping. If we were to go back to this right here, we're down in this range right there. If that's 1, 0.1 right here, we're pretty low, right? So that's like the linear damping that we can expect. So now let's see, we'll change over to baby blue and find the log decrement from 2 pi damping factor divided by 1 minus damping factor. And by the way, that's the same equation that's right there. So 2 pi times 0.06809. And that's going to be right, actually right there is going to be pretty close based on what we said right here, because this is, we'll say that that's sort of a linear type of thing where the numerator pretty much is in charge and the denominator is pretty close to 1. But we'll go ahead and do that. We'll see 1 minus 0.06809 squared. You can see, because that squared is going to be a pretty small number in the bottom, so it's not going to, so it won't affect the actual outcome. So we have 0.4288 is our log decrement, and noticeably it has no units, just like our damping factor has no units. These are dimensionless numbers. And we can also, by the way, let's do a little side little thing and go, what if we want del is equal to 2 pi squiggle. You end up with 0.4278, right? So there's not a lot of difference right there. To answer the last part of this, let's go with deep red. We want to find the ratio of any two successive amplitudes, right? So what they mean like that is, like, it could be this one to this one, this ratio, right? So that could be x max 2, and this is x max 3, and so forth, is what we're saying. So that using that log decrement, we'll take that log, the definition of the log decrement, which is this right here. And sometimes we'll write this for convenience. We'll say that this is the n, and then this is the x n plus 1, right? That's another way that we can write this, but we will write it out here where we go. X n over x n plus 1 is equal to e to the del, or e to the 0.4288, which equals 1.535. Boom. So you can see from here, sort of quantifying the values of this. And this is not a lot of damping, right? So we're kind of lightly damped right here. We're not nearly as damped as, like, critical damping is a long way away, as we can see from right here, right? Because right here will be critical damping, and we go off, we can see we have like exponential type of thing going on. So that's it for the first example. I'll do the next one will be a one by Dr. Bob.